Hello everyone. Today we'll be moving on with chemical periodicity of chemistry, CIAS or AL chemistry. I've split this lesson into three parts and merged them also with group 2 and group 17. So the first part will be covering the general periodicity, which is mainly across the third period in our syllabus. And then in the second part, we'll talk more about the trends in group 2. And in the third part, we'll talk more about trends in group 17. So in today's video, we'll be covering the trend of the atomic radius across the period and down the group, the trends of the cationic radius and anionic radiuses, radii across the period, the melting point trend across the period, reactions with oxygen and their observations, reaction with chlorine, reaction and dissolving in water, and along with their chlorides, and a brief overview of the acid-base characteristics of metal oxides along with some of their uses, and lastly the aluminium amphoteric characteristic. So let's begin. Now to begin with, periodicity in the lesson periodicity, we'll be talking mainly about elements in the third period. Now you don't have to know every element in the third period because you'll be provided with the periodic table in your data booklet, but it basically means that every element from sodium to argon. Now sometimes they'll ask you questions for other periods, but you will have to use your knowledge of these trends to answer those questions in your exam papers, because in reality the trends are very similar, but they're not exactly the same, but just assume that they are the same whenever you're answering. Anyway, so let's move on to the first part, and that is the trend of atomic radius across the period. So the trend of atomic radius across the period is very similar to the trend of first ionization energy across the period, across the third period. So whenever you're referring to the third period, like the atomic radiuses across the third period, you have to refer to the same things: the the nuclear charge due to the number of protons. Then you have to refer to the distance of valence electron from nucleus and the shielding effect. Okay, and what the atomic radius is basically, so this is the proton and neutron, so this is the nucleus, okay, and this is the first shell and this is the second shell, okay. And what the atomic radius is basically the distance between the center of the nucleus and the last or the valence shell. So basically where the valence electron will be present determines the atomic radius of an atom. I hope that makes sense. So it relies on the same terms, or relies on the same factors as the first ionization energy. The only difference being that there are no exceptions. Like in the first ionization energy, there's an exception between Mg and Al, and there's an exception between phosphorus and sulfur, and that is because of the differences in energy levels and the valence electron pair repulsion. But in first across the third period for the atomic radius, there is no exceptions. So this is how it goes. So this is across period, and this is the radius. So the radius goes something like this. So whenever you're asked to explain why across the period, that like whatever this is, so what you have to say is across the period, atomic radius decreases because increasing nuclear charge, but the electrons are added to same shell. Therefore, shielding effect is constant, and so greater nuclear attraction, therefore decreasing distance between outer shell electron and nucleus. Now this is how I'd write it. You can paraphrase it, but the points must still be the same. You must refer that across the period atomic radius decreases because of an increasing nuclear charge, but because electrons are added to the same shell, the shielding effect is constant. The greater the effect of nuclear attraction and therefore decreasing distance between outer shell electron and nucleus. That is pretty much what it is. That is pretty much what the trend is across the period. Now, along with trend of atomic radius across the period, you also have trend of atomic radius down the groups. Down the groups. And that is much more simpler because down the groups, you know that despite the increasing nuclear charge, more shells are added, like more principal quantum shells, and therefore increasing distance between the outer shell electron and the nucleus. And there's also an increase in shielding effect, and therefore the the atomic radius decreases down the group. Now, whenever you're asked to explain like changes in atomic radius or first ionization energy as well, you always have to refer to or comment on these three. And as long as you're able to make a correlation between the trend of radius and these three factors, then you should be able to answer them correctly most times. Most probably all the times as well. But yeah, most times you should be able to score all the marks in such questions. Now let's get a bit more things get a bit more complex here. Now let's talk about the trend of cationic and anionic radius across this period. So the first three metals are sodium, magnesium, and aluminium across the third period, right? Now, the how would the atomic radius, not the atomic, the cationic radius, and what I mean by cationic radius here is the maximum oxidation state possible. So the most positively charged cation of each of these elements. How would the cationic radius of those vary across the period? So in case you don't understand, Na plus, Mg2 plus, and Al3 plus. How would the cationic radius vary across the group for these three ions? You can pause the video and think for a bit if you want. Anyway, as you can see that across the period, let's think about it. Okay, across the period, the nuclear charge increases, okay, and the shielding effect. So when these three electrons are removed, the shielding effect is decreased, right? Now, for all of them, sorry, across the period, the nuclear charge increases and the shielding effect is decreased. So which one will have a lower or smaller cationic radius? And the answer is Al3 plus. So across the period, the how do I say this? The cationic radius decreases. And why is that? Because of this term, stronger effective nuclear charge. Now, what is stronger effective nuclear charge, you may ask? Well, what stronger effective nuclear charge basically is that, so let's say for Na, right, we have how many electrons? 11. So when one electron is removed, you have two shells of 10 electrons and you have 11 protons, right? So the charge is plus. Now, those 8 outer shell electrons are attracted by 11 protons. For Mg, the outer shell electrons are attracted by 12 protons, and for Al, the outer shell electrons are attracted by 13 protons. So the effective nuclear charge basically is that uh, because of the higher positive charge, there's a greater attraction between the valence electrons of the one shell lower. Uh, there's a stronger attraction because of the greater positive charge. I hope that makes sense. So across the period, there would be a decrease in cationic radius. Now, how about anionic radius? What would be the case for anionic radius? So across the third period, the anions would be, I'm talking about their, okay, so P3 minus, S2 minus, and Cl minus. So how would these vary across the period? So across the period, Cl has 17 protons, this has 16 protons, and this has 15 protons. So when electrons are added, these 15 protons have to uh, attract have to what? Yeah, right. So these 15 protons have to attract three more electrons, right? Whereas for this, the 17 proton attracts only uh, one more electron, and electrons are added in this case for anions, not taken away, right? So across the period for anions, nuclear charge increases, right? And shielding effect is constant because no electrons are added to the inner shell. It's reasonably constant. But what happens is, across the period, there's a decreasing. Oh, sorry, no. Across the period, there's a increasing effective nuclear charge, right? Oh, sorry, nuclear charge. And therefore, across period, increasing anionic radius. You could also refer to in terms of the charge. So the lesser the negative, the stronger the forces of attraction, right? Now there's another comparison. There are two other comparisons that you have to be able that you have to know how to make. The first is between the respective ions and atoms. So for metals, for example, Na and Na plus, and also for anions, Cl and Cl minus. So for Na and Na plus, this has a smaller R value. Why is that? And that's because an electron is removed, so it has one lesser shell, and therefore the radius is much smaller than that of Na, the atom, because it has one more one more principal shell. Whereas for chlorine, this has a higher radius, higher R value, right? Why is that? And that's because both have 17 protons, right? But in this case, these 17 protons are trying to hold together 18 electrons, whereas these are holding only 18 electrons. And therefore, the comparison between an atom and an anion is that there is a lesser or weaker effective nuclear charge. I hope that makes sense. And the other comparison that you have to be able to make is a comparison between anions and cations. So what would be the case, for instance, Al3 plus and P3 minus? What would be the case? Similar to the previous example given, or the previous examples given, it's the same here. When cations and anions were involved, you recall that in cations, in the same period, in cations, one shell is removed, whereas in anions, electrons are added to the same shell. No shells are removed, and therefore cations in the same period have, what do they have? Smaller R value, and that is because one less principal quantum shell, and therefore decreasing distance between valence electron and nucleus. Over here you can also make reference to the effective nuclear charge. You can also make reference to the shielding effect, but that is not really necessary. You just have to understand it in brief. I hope that makes sense. Now that's all there is for the atomic and anionic radiuses. Sorry, anionic radii. Now another thing that's important, a trend that you have to know, is regarding, as mentioned before, just give me a minute, let me scroll up. Yeah, so another thing that you have to know about is the trend in melting points across the period. And for this, I have taken a graph directly from your textbook, the chemistry textbook that's given to everyone. There's PDFs available online as well if you do want. If I find it, I'll link it in the description of the video. Anyway, So this is the trend in melting points across the period, third period. And you see that across the third period, there is firstly an increase in the melting points. So from sodium to magnesium and then to aluminium, there's an increase, and then there's a major increase. The highest is in silicon. And then there's a huge decrease, and then sulfur, chlorine, argon, there's a huge decrease. Now you have to be able to comment on these trends, like why this is the case. So the comparisons that are usually made involve like why these are higher than like the non-metals, right? And over here you have to mention that these are held together by IMFs and that these have giant metallic structure. Metallic structure, and therefore have stronger electrostatic forces of attraction between have electrostatic forces of attraction which require more energy to break. Again, this is the reason why the metals have a higher melting point than the non-metals. Okay, and sodium is a group 1 metal, and therefore it has a much lower melting point. It's much more reactive, as you recall from the alkaline metals in your IGCSE years. Now let's move on to why silicon has such a high melting point. It's even higher than the metals. It's obviously higher than the non-metals. And the reason why silicon has such a high melting point is because silicon is a tetrahedral structure that has a giant covalent structure. This is very important. And because this has such a giant covalent structure, requires most energy to break extensive covalent bonding between between the Si atoms. Now, if you recall from your previous lessons that I taught, it's that for nonmetals in general, the simple molecular ones, the only thing you have to do is break or weaken the IMFs, which are much weaker than the bonds holding than the regular bonds, which is ionic, covalent, and metallic. But in Si, because it's a giant covalent structure, to cause it to change shape, you have to break the covalent bonding, break or weaken the covalent bonding holding the Si atoms together. Now, because the Si, the bonding is so extensive, you have to weaken or break a lot of them, and that's why the net energy required to break all of them is much higher than that of metals and also that of non-metals, right? And I've never seen a question being asked, but it's not within your syllabus, but in case they do ask why the increase over here is much lesser, all you have to do is comment on the increase, like the increase in electrons being less significant, or when there's a second electron, and like you have to make a comparison between Na and Mg and Mg and Al. When there's 2 electrons versus when there's 3 electrons, the effect is much less significant when 1 electron is added to 2 than when 1 electron is added to 1 electrons. Okay, that's what you have to comment on in case they ever ask regarding why the increase is much less here. Anyway, now another important thing from the same graph is this. Now you may wonder why sulfur has higher melting point than phosphorus and then chlorine, and this is mainly because of the strength of van der Waals. Now these in like their original state, in their original form, they won't have any other IMFs than van der Waals because they do not have they're not polar because they're the same atoms, and therefore no bond polarity is established, and they cannot have hydrogen bonding either because they're not directly bonded to a hydrogen atom, right? Therefore, everything is because of the strength of van der Waals. Now, the reason why I'll give you the original forms of these. So this exists as P4, this exists as S8, this exists as Cl2, and this exists as Ar. Now, if you make a correlation between the factors in influencing van der Waals, you can make a proper comparison. Why the melting point is something like this: S8 greater than P4 greater than Cl2 greater than Ar. And that is because across this trend there is a decreasing number of electrons, therefore decreasing strength of van der Waals forces, right? So requires much less electrons to break. So not much less electron, much less energy to break or weaken. And that is why the trend is like this for the nonmetals. Now that is it for the trend in melting points across the third period. Now we'll move on to okay, wait, I'll just scroll down. Now we'll move on to the reactions of third period elements with oxygen and their observations. Now these are some, like, the next few things are very theoretical, like as in all you have to do is remember them. You don't really need to understand anything behind it, you just have to know the observations and what happens. So let's just note down some of the third period elements. I won't be balancing the equations, I'll just write it as it is. And there's Mg, then there's Al, there's phosphorus. Okay, wait, I'll just make more space. So Na, Mg, Al, then there's phosphorus. No, before phosphorus there's silicon. And then there's phosphorus, sulfur, chlorine, and argon is monoatomic, so it won't react with anything. So anyway, for sodium, it'll react with oxygen to give Na2O. That's sodium oxide, and the reaction is very vigorous, and the observation is yellow flames. From your IGCSE years, I think there was a section where you had to recall the flame tests. Lithium is red, sodium is yellow, and potassium is lilac. For Mg, it'll be MgO, and the flame is bright white. Bright white flames. For Al, which will give Al2O3, it just glows. That's the observation. For silicon, it'll be SiO2, and the observation, I don't think there is much of an observation apart from it's a slow reaction, and that SiO2 has a very high melting point. For phosphorus, the thing formed is P4O10. You have to write it like this, P4O10. That's the original state of it, and it can either give yellow, not either, it gives a yellow-white flame. For sulfur, it gives SO2, and this is a blue flame, very gentle blue flame. And for Cl, well, Cl does not usually react with O2, so we don't have a reaction for this. The important ones are this. No, wait, I'll just this, and this. They rarely ask about this, and they rarely ask about. Yeah, they just basically never ask about yellow-white flame. I've never seen this asked. But apart from that, everything over here you need to know. And the slow reaction, I've never seen this asked as well. But it could be asked in an earlier paper or the more recent papers. It's best to know everything anyway. And that is the reaction with oxygen. Now let's make the reactions with, just give me a minute. The reactions with chlorine. So the reactions with chlorine are also, I won't balance the equations. So the reaction with Na and Cl2 will give you NaCl, table salt, basic. With MgCl, it will give you MgCl2. For AlCl, it will give you AlCl3, which is hydrated, or will give you Al2Cl6, which is anhydrous. Okay, for Si, it will be SiCl4, and for P, it can either give PCl3 or PCl5, depending on the oxidation state of the phosphorus. And there generally isn't a reaction between S and Cl, so we don't really write that. If there is a reaction, they mention it in your paper. Now we move on to the reactions with water. Again, this part is purely theoretical, so these are just things that you have to remember. You don't really have to understand much in depth. So reaction with water. So with NaMg, and I believe, okay, yeah, so reaction with water. So Na plus H2O would give you NaOH. Recall that OH is minus plus H2 gas. So the observation is that there's effervescence of H2 gas, and with Mg, it depends. So in cold conditions, it would give MgOH2 plus H2 when it's cold, and in hot conditions, like when there's steam, it would give MgO plus H2. So hot or steam. You have to remember this. This is very important. I've seen this asked many times. And another reaction is P4O10 plus H2O, which would give you phosphoric acid, H3PO4. So it's an acidic solution. And phosphoric acid is a weak acid. And the reaction of SO2 plus H2O directly would give you sulfurous acid, H2SO3. Yeah. Now, the reactions, let's move on to, it's still under the same topic, but for NaCl and MgCl2. So unlike PCl5 or PCl3, okay, wait, first I'll write SiCl4, H2O. When you have a reaction between SiCl4 and H2O, what will happen is hydrochloric acid will be given out and silicon dioxide. Same is the case when you react PCl5 plus H2O, you would get phosphoric acid, I believe, and you would get HCl. I have never seen this being asked in the syllabus, so you don't really need to remember it. However, there's a difference between reaction and dissolving. So these are reactions. But when you try to react NaCl or MgCl2 with water, you won't get a reaction, but you'll get more of a dissociation. So when you do NaCl(S) with water plus AQ, what would happen is it would dissolve in water. So it would form Na plus AQ plus Cl minus AQ. It would form aqueous ions in the water. It get dissociated. Same is the case with MgCl2 plus AQ. It would just dissociate in water to form ions, AQ plus 2Cl minus AQ. These aren't reactions, these are dissolving. And the important thing that you need to remember between these is that the pH when sodium chloride dissolves in water is 7, and the pH when this dissolves in water is 6.5, approximately 6.5. And in this case, the pH would be around 1 to 3, like 1 to 3, because HCl is acidic, H3PO4 and HCl are both acidic, right? And for Al, whenever aluminium or aluminium chloride or aluminium trichloride dissolves in water or reacts with water, it forms an acidic solution with a pH of approximately 3, I believe. And the reason for that is Al forms a complex H2O6 You'll get more into you'll get more of an idea of complexes in transition elements in A2, but what happens here is when it forms a complex, recall that an acid is a proton donor, and so this can AlH2O5 OH, right? And it'd be 2 plus because 1 is gone, and plus H plus. So it can give off a proton or an acid or an H plus, and therefore this forms an acidic solution of pH 3. That's what you have to know. And regarding a bit of acid-base characteristics, the reason why okay, first of all, the reason why MgOH2 or NaOH are basic, as in they react with acids to neutralize them, is because the OH minus can accept H plus. Bases are H plus acceptors, can accept H plus. So when this accepts H plus, it just forms water, which is neutral in standard conditions, and therefore these are basic. The case with MgO or Na2O, the reason why these are basic is because O2 minus in these compounds can react with H plus as well to give two no wait, what does it give? Right, it gives 2 OH minus, and that is why these are sorry, wait a minute. The reason why these form basic solutions when dissolved in water is because when O2 minus reacts with H2O, like when dissolved in aqueous water, it forms 2OH minus. And you come back to this, that 2OH minus, OH minus can accept an acid, not an acid, sorry, an H plus, and therefore it becomes basic. That is the reason why MgO and Na2 or oxides of metals are typically basic. But there is an, no wait, before getting into that exception, what you have to know is that when MgO has a use, and this use you have to remember is that it is used in lining of furnaces. I've seen this asked in a past paper question before, and the reason is because insulators and can withstand high temperatures. And the reason why they can withstand high temperatures is because ionic bonds and giant ionic lattices therefore requires a lot of energy to break the bonds, right? Anyway, we move on to the last part of this lesson, and that is aluminium amphoteric characteristics. So unlike oxides of previous, so from Na, Mg, Al, Si, going on, there's phosphorus, sulfur, and chlorine, right? Well, there's no oxide of chlorine, so the oxides of each of these, so sodium, magnesium, of the metals, sodium, magnesium, they are basic. Whereas for these, they're acidic, right? But Mg is a special case. Why? Because it is amphoteric, meaning it can act both as an acid or base, depending on when it's required. So for instance, Al2O3, right? The oxide, which is basically Al2O3. When reacted with H2SO4, no wait, let's take a much more simpler acid, Cl, we'll neutralize this to form a salt and water, so which is AlCl3 plus H2O, right? So see, it neutralized it by accepting an H plus, and it formed water. Same is the case for if it reacts with a base. Now, when reaction with a base, all you have to know is that when it reacts with a base, it acts as an acid. And you also have to remember an equation, and a basic equation this is unbalanced, so I'd request you balance it yourself. Al2O3 plus NaOH is a typical base that's used. When it reacts, it forms NaAlOH4 plus H2O. So this is Al2O3 acting as base, and this is it acting as an acid. That is all there is for this lesson. I hope you understood. If you do have any doubts, please leave them in the comment section below.